Hello everyone, welcome back to another very interesting video. This particular question is also taken from Pathfinder book and the chapter is System of Particles. Very nice ideas we are going to discuss, definitely very useful for our examination point of view, advanced exam. Okay, let's get into it. Let me read the question first. A cylindrical beaker is held at rest, okay, with its bottom horizontal and inside it a large number of identical elastic balls are moving up and down. So this cylinder is filled with elastic balls, not fully, maybe partially fully, but we'll understand it as we go on. But the number of balls are very large, that means each ball is like very small. You can treat them like molecules like, okay, and they are identical and also elastic. They are moving up and down continuously, colliding with each other and also with the bottom. Actually, when the balls collide, they will have some oblique collisions also. They don't move only up and down, they will move even sideways also. But they mentioned up and down only here. Let's understand it as we go on. In this way, the balls fill the beaker up to 750 milliliter mark. So as they are moving up and down, they are able to go only up to 750 milliliter mark, not beyond that. Let's say this is a cylinder. The cylinder was not given in the question, I just drawn it so that you can understand. The balls are able to go up to 750 ml, not beyond that. Why they are not able to go beyond that? Probably because of gravity. Let's understand, because they said horizontal. No? So gravity effect also should be considered here. Okay. At some random moment, the beaker is made to move downwards with an acceleration 0.5 g. Okay, very good. So there is gravity and also now the container will have acceleration as well. Here g denotes the acceleration due to gravity. What fraction of total number of balls will now fill the beaker up to 1125 milliliter mark? So this is 750 ml, meaning somewhere over here you will have 1125 ml mark, and at 1125 millimeter mark, up to that much how many balls will remain when the beaker starts moving down with the acceleration g by 2. That's a question here. So this question seems to be related to kinetic theory of gases also, system of particles, kinetic theory of gases. In fact, when we study theory of molecules and try to understand the temperature at microscopic level, we use certain assumptions like elastic collisions and so on. So I feel that as we go on, we'll understand that this is somewhat related to even KTG, like system of particles idea, KTG. So that's the assumption I'm getting as we go on. And they said it is also having acceleration container. So let's try to explore this question one by one. First and foremost, as I understand this question now, what I feel is certain assumptions we can go on with, some hypothesis. First assumption is that n is very large, they said that, and of course it seems like KTG. So probability statistical also we might want to use if required, but right now I am thinking that it might be required also probability. So n is very large, then what happens? Probability becomes reality. When you take a large number of trials, the reality will approach, the probability will approach reality, that you know it. So this idea I might want to use because I feel that it is related to KTG. Okay, that's one point. The second point is horizontal velocities, they didn't mention also, and in fact here horizontal velocities we don't need to worry about because they were talking about movement up and down, right, up to 750 ml. Even though they will have horizontal velocities, we are not going to discuss about this because they are not required to analyze what was asked here. So that is a second point we need to take it into. And this is the third point is idea. This idea is very simple, but I want you to take my perspective also and see whether it matches with you and see whether it is convincing or logical to you. When you have two bodies, identical bodies, having a head-on elastic collision, you know that their velocities get exchanged. That's a very basic idea. But the same thing can be assumed in a different way also. Just focus on the velocity vectors alone, not the balls, but velocity vectors if you focus on. You see that yellow color velocity V1 would go down, it will get transferred to the next ball, and red velocity which is already up, it will go up only. So the V1 would survive even after collision, but just that it is getting transferred to another ball. It is not in the same ball, but it gets transferred to other ball, but it will continue like that. So even if you have multiple collisions, the V1 will continue to get transferred from one ball to the other ball, and V2 will get continue to transfer from one ball to the other ball. So the collisions will not affect that velocity vector. If at all it is going to be affected, it is only because of gravity. So the collisions between the balls would not affect the velocity vector as such, just that they get transferred from one ball to other ball, and we know that they are identical balls. So whether this ball or that ball, I don't care. One ball has that velocity and that is moving up because of gravity. So because of that assumption, and even in KTG also we neglect collision between the molecules. So here also we can neglect the collision between the molecules because they are not going to affect this height up to which the balls will reach. So that is one more thing I want to emphasize here. Important idea even in KTG. Next idea, in a region of higher vertical velocities, the density of molecules or the balls will be lesser there. I hope you understand it pretty well. Let me give you an example also. Imagine there is a car racing happening. So whenever this track is straight, you see that cars would go much faster, and there the density would be lesser, meaning they will be far apart. But whenever you see the curved end where the cars slow down, and you see the cars will get crowded there, so the density is more. Same idea you can understand here. So wherever you have higher velocities, that's where you will have lower densities. So in the cylinder, if you consider, they'll be moving up and down. Okay, the lower side you will have higher velocity, so there the density would be lesser. As you go up, the velocities will be less, so that there you will have more density. That's the idea I want to emphasize there. Next, one more logic is, because it is cylindrical region, you know that volume would be proportional to height. They gave volume that 725 ml, 750 ml or 1125 ml, whatever it is. So that height only we need to focus on, because gravity will affect only the height there. Volume is proportional to height, and that maximum height will be proportional to initial velocity square by 2g. So we are talking about g here. When the container was stationary, g is okay as well. But when the container is moving down, with respect to container, we need to consider effect to g, that will be g minus a, which is going to be g by 2. So the volume in turn will be directly proportional to 1 by g effective. Using that idea, I can take the ratio V naught dash by V naught equal to 2 you will get. That means earlier it was 750 ml, now the volume would go up to 1500 ml. That means the balls which were going up to 750 earlier, because of the container acceleration, g effective has decreased, so it goes up to 1500. It's like somebody jumping on the Mars. On the Earth you jump up to certain level, in some other planet you jump much higher there because of the lower gravity. So that's the basic idea. That means the balls will be spread up to 1500 ml. Now they are saying up to 1125 ml, how many balls will be present? Okay. Now if you focus on this volume difference here, 1500 is maximum it can go up to, and 0. In between they are talking about 1125 ml mark. If you look at the gap between 1500 and 1125, that is 375, and 375 3 is 1125. So this 1125 is 3 times. Because volume is proportional to height, heights also would be in the ratio 1:3. So if this is delta H, this will be thrice of delta H. So the height ratio in the region 1 and region 2 is 1:3. The moment I saw that it is 1:3, immediately I got one idea from the kinematics. We know that in kinematics this is a very simple result. Whenever acceleration is constant and you are releasing from zero velocity, that if you consider the motion of it at equal intervals of time, delta t1 equal to delta t2 and so on, corresponding displacements will be in the ratio 1:3:5. I am sure you are aware of it. And now if you apply here, it is starting from rest at A, where at the maximum height velocity will be 0, and you have g effective g by 2 constant. So at equal intervals of time, it is going to have a displacement 1:3. That means in the region 1 and in the region 2, a ball at the particular velocity vector, if you consider, it will be spending equal time. So that's the point I got here. So each ball on an average, now we are talking about so many balls, on an average if you focus on, they spend equal amount of time in the each region. Of course, some balls will spend more time, some balls will spend lower time. On an average, if you consider, the number of balls are very large, so they spend on an average about equal amount of time in the region 1 and also in the region 2. Now when you come to probability, at any one particular moment you consider one ball, and what is the probability that the ball would be in the region 2? They are talking about this height rising. what is the probability that a given ball would be in the region 2? That is going to be 1 by 2. That's what my statement is. See whether you agree with it or not. So the reason is that any moment the ball could be either in the region 2 or region 1. So it has got equal time possibility. Let's say large number of photos you take, about a million photos you take. At one instant in one photo it is in region 1, another instant it is in region 2. If you take very large number of photos, it is likely that the number would be same because it is going to spend equal amount of time in the region. And from there you see that from probability basic definition, it is equal to number of favorable event divided by total number of events. Number of favorable event meaning number of balls that are present in this region 2, because that's what we are focusing on. Region 2, up to region 2, how many balls are present? That's a question they were asking. Number of balls in the region 2 divided by total number of balls, that is given as half, meaning the number of balls present in region 2 will be 50% of it. So I hope you understand. The question has really become very interesting because we are supposed to use even probability also. Initially when I started this question, I didn't know how it goes, but then in the end, luckily everything comes out to be good. But definitely this question is motivated by kinetic theory of gases assumptions ideas. So I hope you enjoyed it. So with that I'll conclude here. Thank you very much for your time. Until next time, goodbye.